Okay, so thanks for having me. I'm not gonna say good morning because it's not morning where you are. I'm just in the New York time zone, so it's a pleasure to be part of this initiative at Crunch DAO, and I'm really pleased to have the opportunity to share with you some reinforcement learning knowledge, which has been the core of my research for some years at this point. And today I'm going to give you an overview of what reinforcement learning can do for finance and in general for quant finance. So the presentation is more or less divided in two parts. The first part is going to be about like what reinforcement learning is actually doing when you're trying to solve a problem. And then there will be a simple application taken from one of my papers to give you an idea what reinforcement learning can do in finance, and also what are the issues, because there are some issues that need to be tackled when applied to this particular domain. So as you see, the title of my presentation is saying that this is a data-driven approach. So what makes reinforcement learning different from other kind of control techniques is that you're really data-driven, and now we're gonna see how. So the agenda for today, as I said, is I want to motivate a little bit why we would like to use reinforcement learning in finance and economics in general. So in the realm of social sciences, it's very interesting to see what reinforcement learning can offer. And then I'm going to dive into some basic reinforcement learning notions and some rough idea of how you can divide family of algorithms, so that if someone never seen reinforcement learning before, can start getting familiar with the idea of what is a reinforcement learning algorithm and what are the different categories that group them. And then there will be like an application to benchmark reinforcement learning on a simple trading problem. So let's start trying to motivate why reinforcement learning in the financial domain. So first of all, reinforcement learning, it's a branch of machine learning. It's a paradigm, and it's different from the other paradigm that you may already know, like supervised, unsupervised. It offers some other opportunities, but it also comes with other challenges. In general, you may want to use reinforcement learning when you want to solve a problem that has sequential decision making over time. So whenever you have the time component, reinforcement learning can be useful to solve your problem. And as you probably know, the financial domain is full of problems where you have to take decisions over time, and therefore it seems to be the perfect paradigm of machine learning to be applied in our domain. So this is one of the topics that I'm going to touch today. And the other one is, how do you connect the use of neural networks with reinforcement learning? Because one thing that needs to be clarified is that reinforcement learning takes its roots from optimal control and dynamic programming. So something that was very established in the mathematical community, even from the 60s. And so what happened is, as soon as neural networks become more popular with solving computer vision tasks at the beginning of the 2010, they've been started to use also reinforcement learning, and that really helped in improving the subject. So I would say that in the last 10 years, we have seen coming to the scene this new family of algorithms, which are called deep reinforcement learning. So whenever you hear about deep reinforcement learning, we are talking about the usage of some reinforcement learning techniques that still have a lot in common with what was used before, but there is the involvement of neural networks. So what I'm going to touch today is what's the connection, where those neural networks come into play in helping solving a reinforcement learning problem. Now, I want to give you a little bit of an idea of what is the difference between reinforcement learning and another machine learning paradigm. So with the difference with supervised and unsupervised. first of all, when you solve a reinforcement learning problem, you don't have labeled data. So it's not like in a supervised setting when you want to map a certain type of input to an output and you already know the response. So it's just about learning a function that maps from X to Y. In this case, you don't have labeled data. But I will say you don't even have a predefined data set. Because we are going to see how the data set is constructed when you solve a reinforcement learning problem. So it's not that you just missed the label, you missed the data set too. So it's not even closer to an unsupervised learning task. It's really something different. And the peculiar setting where you may want to apply reinforcement learning is when someone has to take actions over time, and those actions cannot show an immediate impact, so they have the so-called delayed effect. So what happened is, for instance, I execute some trades today, but my trades could have a delayed effect in, I don't know, 1 week from now, 1 month from now. So it's important to have a paradigm that can take this into account. So it's not a greedy maximization where we just maximize our objective function at the same at each timestamp, but there is this notion of delayed effect, as we will go to see. And yeah, the last point I already mentioned, that is RL is very suitable when you want to solve decision-making problems that has the time component. So there is this notion of sequentiality. Before diving into the math, I want to show you this, which is the classical RL loop. It's a very basic RL loop. The good part of it is that what you see in this plot holds for every reinforcement learning algorithm, from the most simple to the most complex. Still, this is the structure. So whenever you solve a reinforcement learning problem, you have an agent and an environment, and there is this interaction between an agent and an environment. Now, how does this interaction work? Essentially, an agent observes a representation of state, and the state can be any type of information that the agent can observe. And based on that information, the agent can take an action. This action is sent to the environment, and the environment can respond with a subsequent representation of the state, because maybe when the agent took an action, it modifies the state, or in other words, the state can change. The set of information can change over time, as also happens when you solve a supervised learning problem, for instance. But the other, probably most important part in the RL loop is the R. R stands for reward. The reward is the feedback that the environment is sending to the agent, and that allows the agent to evaluate how good was the action that took. And this is important because this loop keeps going on and on. And when I told you that when you solve an reinforcement learning problem, you don't have a predefined data set, this is what I meant. It's through the agent environment interaction that you build the data set. And the data set consists of sequences of state, action, subsequent state, and reward. So it's always a tuple of 4 elements, which you use to update your policy. Now we're gonna define all of these elements in a much more formal way, but this is the idea. So you don't have label, you don't have a predefined data set. What you want to do is to let your agent interact with the environment and collect information. But so far I've been very general. I've been talking about agents, environment. What can they be in a quant finance setting? It's important to put this into perspective. So in this slide, I listed a definitely non-exhaustive list of application that you can do in quant finance, but it's going to help us in order to understand how you can frame the reinforcement learning problem for practical challenges that one can face in quant finance. So for instance, you can use RL for trading and portfolio management, portfolio optimization. And in this case, you're going to have an agent, and your agent can be the trader or the portfolio manager that has to learn a way of make trade or allocate the capital with a given goal. And the goal is exactly what the reinforcement learning agent wants to maximize. So the goal can be expressed by the reward function that I was that was showing to you in the previous plot. But obviously, trading is the most intuitive, because if you think about trading, you think about the fact that you have to do some trades over time, and it's very natural to think about the RL paradigm, but it doesn't end here. There could be market making application. For instance, RL is very popular for execution problem. So whenever you know the side and the size, but you don't know when to execute your trades, you can solve an optimization problem in a data-driven manner using reinforcement learning. And as well as if you have complex derivatives in your portfolio, you can devise a complex hedging strategy in a data-driven manner. So putting in a perspective of you are the portfolio manager and you had to hedge this position. It's just a matter of modifying some elements of the reinforcement learning loop, defining them in a proper way to solve your problem, and then you're good to go. You can solve your problem. So as you see, all of those tasks, what they have in common is they had the time component. So there are some actions that you had to take over time in order to reach your goal. So now I'm going to start introducing what are the components of the RL loop in a much more formal way, so that I can give you an idea how those problems can be solved. And obviously, when you apply RL to the quant finance setting, it's much more complex than just defining the elements and running the algorithm, because as you know, as well as it happens in supervised learning, whenever you deal with financial data, you have all of the problems of non-stationarity, you have regime changes. So those are things that largely affect RL and also motivate the last application that I'm going to show you today. But let me start to talk about a little bit more in detail what are the components that I mentioned. So as I said, the most important element in a reinforcement learning algorithm is probably the reward, because the reward gives a measure of the agent's performance. So the agent takes an action, and based on that reward can evaluate how good that action was. The fact that there is a reward implies that the presence of the so-called exploration exploitation trade-off, because what could happen is you could have your reinforcement learning agent just maximizing the reward at each point in time, and this is going to be just exploitation. In that case, your reinforcement learning agent is going to act just in a greedy manner. When instead, what you want to have, since we mentioned that there could be the existence of delayed effect, what you want to have is an agent that also explores from time to time. So there is definitely a trade-off very known in the reinforcement learning literature, which is exactly a trade-off between explore a little bit, taking actions that are suboptimal, trying to explore the state space, because always acting greedy is not necessarily the good way to do so. But we define this scalar signal because at the end of the day, you define the goal of the reinforcement learning agent as the cumulative discounted future reward, which is this G. So G is just the sum of all of the rewards over time, discounted with a discount factor gamma to avoid that the sum goes to infinity. Then moving on, we mentioned that an agent observes a set of information, which in the most simple case can be a vector of information. It's a vector of input. It's, I will say, similar in some way to what could be the set of input in a supervised learning setting. So it's like what you're showing to your supervised learning algorithm to learn the mapping from X to Y. In this case, is what you're showing to the agent in order to be able to take an action. So state and action are closely connected, and what connects them is a policy. This policy pi, reflects the behavior of the agent, and it's in general distribution. It can be deterministic, so it can be just a function of the state that gives you the action to do, or it can be stochastic. So it can be something that it's a distribution of action given a certain state. So as you see, now we are introducing already a difference between the type of problems that a reinforcement learning can solve. It can solve problems where the policy to learn is deterministic, but also stochastic. So I'm being very general here, trying to leave open all the possibilities, and I'll be more specific later on with the application. The last core element is the value function. The value function is something that you can use to measure the goodness of being in a certain state and taking a behavior according to a policy. So obviously, it's not enough to have the scalar reward. You also need to have a way to evaluate the fact that you are in a certain state and you're obtaining that reward. And value function allows you to make this evaluation over time. So essentially, this is the state value function, the v pi, which is a function of the state, and is defined as the expected value of the cumulative sum of discounted reward, G, that we just defined above, conditioned on the state where you are. So essentially, it's like saying, given the state that I'm observing at this point in time, if I follow the policy, pi, this is going to be the expected cumulative discounted future reward that I'm going to obtain. And value functions are very important for the reinforcement learning problem. Because what we are solving here, the goal, the optimization problem that any reinforcement learning algorithm is solving is trying to find the policy pi that maximizes the expected value of G. And the aim is exactly learning a behavior, which can be deterministic or stochastic, to maximize this sum of scalar values. And G reflects the long-term objective. As you see, it's a sum of discounted rewards over time. So that's where the delayed effect comes into play, because what you're maximizing when you solve a reinforcement learning problem, it's not the reward at each point in time, but it's a sum of reward over time. So you always have the long-term perspective. And that's important, because most of the problems that I mentioned before, they always have a long-term objective. If you try to solve them in a greedy manner, you're not going to get good results. So talking about value function, there are two types of value function actually. The first one I just defined that in a previous slide, which is V. V is called state value function, and then there is a Q, which is called action value function. The only difference between the two, as you can see from the definition, is that Q depends also on the action, while V just depends on the state. So the difference in the interpretation is that Q is the expected cumulative sum of future rewards, given the fact that you are observing a current state and you're taking an action A and following a policy thereof. So the only difference is that you don't follow the policy from the very beginning, but you first take an action A and then you follow a policy. And this allows to evaluate the contribution of each action that you can take at this point in time over the expected sum of cumulative reward. And this is important because value function, which they're very connected to the Bellman equation, are important to solve the DRL problem in an iterative manner. Especially, they're very important for the very simple RL algorithms that I'm going to introduce today. So as you see, there is a connection with dynamic programming and optimal control, which it's not necessarily new, which is really rooted in the old mathematical research. And thanks to Richard Bellman, we have the Bellman equation, which essentially gives us a way to evaluate the value function for a given policy, which is expressed as a weighted sum where pi is, as I said, is the policy and is a distribution. So you can weight the contribution of each action given their probability of appearing. And the Bellman equation is important because you can also rewrite that in terms of Q. So the equation 4 is brought in terms of the value function v, but you can also write that in terms of q because there is a connection between v and q, which is explained in equation 5. So essentially, the state value function v can be represented as a weighted sum of the action value function q, where the weights are exactly the probability of occurrence of a certain action, and you're summing over the space of all action. Why are we talking about value function in such details? That is because there is a very important connection between the dynamic programming literature and what is called tabular reinforcement learning. So the type of reinforcement learning algorithm that do not involve neural networks. The difference between dynamic programming and reinforcement learning, and I want to make this very clear because it really helps in understanding why RL is data-driven, is that dynamic programming assumes the full knowledge of the state transition. So essentially, if I go back of one slide, whenever you look at the Bellman equation, dynamic programming is assuming that this P, this probability of being in a state S, taking action A and transitioning to a new state S prime is known. So it's like saying, I'm trying to solve a problem in a given environment where I exactly know what's going to happen if I do a certain type of action and I'm in a certain type of state. And this can be true when you solve very simple environments where you actually know, you either actually know the physics if you're trying to solve a robotics problem, so you know exactly what is going to happen if you execute certain action. But this is not necessarily true most of the time, especially in finance, because it's very hard to know that if you observe a market state and you take a certain action, it's very hard to know where you're going to end up at the next state transition. So you don't have full knowledge. Therefore, RL, which is the type of RL we are talking about, is also referred to as model-free, doesn't assume any of it. So it's like saying the reinforcement learning problem is being solved just by the interaction between the agent and the environment. So there's no knowledge of this state transition. And this is important because what dynamic programming does is to dividing the problem into two recurring subproblems. So solving a policy evaluation first, since the dynamic programming knows that the knowledge of the state transition can at any point in time evaluate all the different value function for each given state, and then doing what the so-called policy improvement, because then you can rank the policy according to the value function that you can compute in a closed form and modifying the behavior accordingly. But if you don't have the full knowledge of the state transition, you have to resort to data-driven techniques. So essentially what happened for a very simple model-free reinforcement learning algorithm, there is still the two-step solution, but they are accomplished in a different way. And model-free RL can have two instances. So you can have a setting where you do Monte Carlo RL. So you collect full episodes of experiences. And that really depends on the problem you're trying to solve. So for instance, if you're trying to edge a portfolio, you probably are going to train an episodic reinforcement learning agent, because what's going to happen is if you have a portfolio of derivatives, at some point they're going to expire. So the edging problem is going to end at some point. So in that case, you can train episodes of experiences where you let the agent interact with the environment for a given set of time steps up to the termination of the episode. And then you have collected the sequences of state, action, reward, and subsequent state representation. And you can use those data to update your policy. On the contrary, they can be also so-called temporal difference learning, which instead can learn from incomplete episodes. Incomplete episodes means that you don't have the notion that I just described of a termination with the kind of problem you're solving. So for instance, you're solving a trading problem, but you don't have necessarily an horizon where you want to stop. You can still solve a reinforcement learning algorithm, a reinforcement learning problem. So you don't necessarily have to have this notion of termination, but you can keep going with your optimization problem, and this is called temporal difference learning. The most known temporal difference learning method is called Q-learning. Everyone that approaches RL probably learned this for the first time. It's called tabular method because in its very essence, what is happening here is you have a table where each entry of a table represents a state and an action representation. And what Q-learning is doing is through this iterative update function is trying to modify the entries of the table, and the table exactly represents the action value function. So it starts with a table that is filled with a lot of zeros, and then the agent starts to explore the possible all the possible pairs of state and action, and every time you update your state value function, you update your table. And once you stop the training, you can use that table as your policy. So this is the idea behind Q-learning. There is no neural network involved. You just have a table, and you keep doing this exploration-exploitation trade-off where you let the agent interact with the environment and you update that table. So what happens when you introduce neural network? You deal with the so-called deep reinforcement learning, which you can refer to also as approximate reinforcement learning. Essentially, tabular array problem. So whenever you don't use neural networks, they have the so-called Castle dimensionality problem. This is common also for dynamic programming problems. And the introduction of neural network helps in order to scale these problems to higher dimensionality. When you introduce neural networks, you can have two families of approximate array algorithms. One, they are called value-based, because essentially you devise the optimal policy indirectly by estimating your value function. So you estimate your value function, and then you have a way to evaluate some way of behaving according to the fact that you know the goodness of being in a certain state and take a certain action. Or you can have policy-based methods, which are more direct in the sense that they don't deal necessarily with a value function, but they just approximate directly a policy function. The reality is that in deep reinforcement learning, it's a very successful method. They are actor-critic, which means that they combine both. So you estimate at the same time a value function and a policy function. And this has been proven to be effective. And if you look at the state-of-the-art reinforcement learning algorithm, most of them, they work in an actor-critic setting. The idea behind using neural network is actually that you want to generalize over unseen states. So instead of the need of exploring all the possible entries of state and action pairs, which sometimes can be unfeasible because you don't have the computational power to explore a very large state space, you can employ very powerful approximators such as neural network to generalize over unseen states. And that's what led to the high success of deep reinforcement learning problem. That's because the introduction of neural network. So just to give some quick examples, whenever you deal with value-based methods, what happens is you parameterize the value function, which can be either the state or the action value function, with a neural network where this theta represents the set of parameters of your estimator, which, as we said, in this case is going to be a neural network. Just to give you a little bit of context and some reference to look at, if you're interested, the most popular value-based methods, the one that gave rise to this field of research, I will say, it's called deep Q network, which is essentially an extension of the Q-learning algorithm, the tabular algorithm, but where this time you don't learn through a table with a lot of entries, but you learn a multi-layered neural network that can take the state representation as the input and return a vector of actions. So deep Q network has been very effective. This is the iterative update that solves the problem. But if you look at the paper that is mentioned in this slide, essentially they started using this approach to play arcade games at the superhuman level, at the level that a human can never reach, because even though you know the rules of the game, you cannot hack in that forward-looking way, as well as the DeepQ network, which then gave rise to a lot of variants, a lot of different reinforcement learning algorithms. So as you see, it's not super recent, but it's not that old. So it's still a very nascent field in the machine learning community. Then moving to policy-based methods, what happened is you don't want to necessarily parameterize directly a value function, but you can also go straight and parameterize directly the policy. So as you remember, the policy was a distribution, was defined as a distribution, either deterministic or stochastic. And in this case, you still have parameterization given by a set of parameter theta. There can be two cases where you want to parameterize a discrete distribution. In this case, you can use a softmax function. So you can express numerical preferences for your actions, and then softmax function is going to give you the distribution of your policy. Or most of the time, when you work in continuous setting where your action needs to be a real value, the policy is parameterized as a Gaussian. So you essentially are trying to learn through an reinforcement learning agent the mean and sometimes also the variance. So you're trying to learn the parameter of a Gaussian so that you can sample action from the Gaussian. And this is proven to be quite effective, because there is a very popular algorithm which is called PPO, proximal policy optimization, which is still nowadays, I will say, probably the state of the art for continuous control in reinforcement learning. So if you have seen recently, the last year, even the way InstructGPT, which is the model behind the wrapper, which is then ChatGPT, use some reinforcement learning from human feedback. And in this case, it's slightly different than what I'm describing here today, but there's a lot of commonality. And if you look at the paper, they're using PPO, so which is a policy-based method. But most of the time, as I said, these policy-based methods and value-based methods are mixed together in an actor-critic setting, where essentially you have an actor, which is the policy, and the critic is the value function. So, and they try to correct each other. So the critic corrects the policy, and the policy then correct the critic. And this has been proven to work well. And even the PPO algorithm that I was mentioning is generally trained in an actor-critic setting. So now I gave you, I will say, a comprehensive enough introduction of the very basics of reinforcement learning. Now I would like to spend some time talking about what are the issues when you actually want to use those kind of techniques in finance. Because, for instance, when you look at solving trading application, the first problem that appears is that it's very hard to benchmark. It's very hard to know if the reinforcement learning agent is actually learning or not. So, because what you have is you could take your real data and trying to set up a trading agent that can look at some market state, some information of the market, and trying to learn from interaction. The problem is that if you don't have a test bed, if you don't know where your algorithm should point, how can you show that those reinforcement learning algorithms are learning? So essentially what we have done in this paper is trying to benchmark the reinforcement learning agent against something that we know well. So for instance, let's take a case where you are solving a problem in a modern portfolio theory on Markowitz, where you know that you are required to forecast future risk and returns, and you also lay down on a set of restrictive assumptions. RL could solve this in a data-driven manner. So in principle, you don't need the forecasting step that is assumed by the modern portfolio theory. So you don't need to have a model for your returns or a model for your risk, because RL could infer the dynamic from the environment. As I was saying, however, it's very hard to assess the quality of this ability to retrieve the underlying dynamic of the market in a data-driven manner. So what we have done is, instead of working in a setting where we lack of theoretical control, we try to demonstrate the capability of reinforcement learning whenever you have a known optimal solution. So the idea is we simulate some financial returns in a synthetic market, and we know that this market follows some rules, which are actually those that are presented in this Garleano and Pedersen paper, and this market admits a known optimal solution. So what happened is we know the optimal solution, and now we're going to see if the RL, without knowing those rules, can retrieve the behavior of this market. So just to give you a quick idea of what this market is, you can have capital N assets at any point in time. The excess returns are described with a factor model, where these factors, they evolve according a mean reverting process. So essentially, you can have the return of each asset described as the sum of mean reverting factors. So there is a mean reverting dynamic in the market. But the way we are going to train reinforcement learning is that the algorithm doesn't know about this mean reverting dynamic. And the idea is, let's see if it's able to retrieve that given dynamic. Also, working in this environment is also costly. And the cost function is quadratic in the traded amount H, and still follow the model of Garleano and Pedersen, and the assumption of the having quadratic cost just follow the transaction cost convexity and the assumption of a linear price impact. So the setting where we are letting the RL environment work, it's quite realistic with because it also includes transaction costs. And the goal at this point is to maximize this objective function, finding the proper set of portfolio strategies over time. So this is going to be essentially what I described at the beginning as the cumulative sum discounted of reward. And if you look at what this equation is, it's actually the risk-adjusted P&L. It's the sum of risk-adjusted P&L over time, where you have the return and the risky part here, and these are the transaction costs. So essentially, this is a setting where you have a known optimal solution, which I haven't posted in the slide. It's just in the paper that gives the title to this slide. And we're going to see if the RL agent is able to retrieve that solution. So what we do is we carry out two groups of synthetic experiments. One where we actually simulate the returns according to the market that I described, where the noise is Gaussian. And if the noise is Gaussian, the optimal solution holds. So we know that if you simulate the returns exactly that way, the optimal solution will hold. And then we can decide to perturb that market representation a little bit to see if, even when the optimal solution does not hold, RL is still able to retrieve a good solution. And that's the idea. If you start with a test bed, and you know that test bed because you know the optimal solution, then you can see if RL retrieved that solution. And after you are certain about that, you can start perturbing the market. And you cannot just change the simulated data. You can also change, for instance, a little bit the reward function by changing the way that the costs are represented. So you can change the transaction cost. You can change also the utility function completely. You can do a lot of experiments in that sense. So our set of experiments, I would say, is just a subset of what is possible whenever you can benchmark reinforcement learning agent. And this gives, even though it's just simulated, it gives an idea of where RL has potential and where RL is having trouble, because you always have the proper response. It's like saying that we are trying to frame the problem in a more supervised setting where we know the answer, but the RL agent doesn't know, and we are able to assess how good it's performing. So in our simplified setting, the action is among of shares traded over time. I'm presenting here examples with just one single asset. So it's the amount of shares traded of the single asset. And the state is defined as the current return that you're observing and the amount of shares that you have in your portfolio. It's a very simplified setting, where the reward signal is the risk-adjusted net P&L. So it's exactly the same function that you have seen in the objective to be maximized in the previous slide. It's just the current reward is not the sum, the cumulative sum discounted over time. And now I have the last two slides of this presentation, which gives us an idea of how good is actually RL in trying to retrieve that solution. So as you see, you have two plots here. The plots on the left represent the results for the deep Q network and Q learning. So you have both a deep reinforcement learning and a tabular reinforcement learning algorithm, while on the right you have the proximal policy optimization, which is a policy-based method. So I divided value-based and policy-based methods this way. The metrics are the net P&L and the Sharpe ratio obtained over time. And essentially, whenever you see the red line, that is the level reached by the benchmark. So the benchmark is an optimal solution. It's deterministic. It does not change over time. Well, instead, you see that whenever you progress over the x-axis, so you're progressing with the training setting, the DQN, which is the blue line, it keeps increasing its net P&L, which means it's learning. And as you see, you have a lot of dots, which are then averaged, because this is very common in reinforcement learning. Even outside finance, you generally train more reinforcement learning agents, and then you average the performance in order to see an average result. And as you can see, even PPO and DQN, which are the blue line respectively on the left and on the right, they can retrieve the level of the benchmark after some period of training. And this is interesting because it gives us an idea of the fact that actually reinforcement learning is learning from interaction with the environment without knowing everything. Because again, whenever I input in the state function just the return and the current state of the portfolio, it doesn't know that there exists a mean reverting dynamic, even though I know that I simulated the data with a given return dynamic. So that is very clear. And but the reinforcement learning doesn't know and keeps training. But I think it's interesting also to look at the fact that DQN, when you look at the P&L, DQN is the yellow line, achieve a suboptimal solution. And this is because of the cost of dimensionality. So essentially, it's like saying, given the amount of period of training, Q learning did not have time to explore enough of the table, which represents each entry of the possible state and action pair. So essentially, the introduction of neural networks, as I was saying, it's very important because you are speeding up the training time. You're allowing your reinforcement learning agent to generalize over unseen states, and that really shows benefit for the learning process. So moving on, what happens if you perturb the market, as we said? So if instead of simulating the data according to a Gaussian distribution, we simulate them according to a student seed distribution with a couple of choices of degrees of freedom. So we simulate a return distribution, which is much more closer to the assumption of heteroscedasticity, where you have factor tails. And still, you see that the reinforcement learning agent is able to overperform, especially PPO can overperform the solution that can be calculated in by the optimal solution of the benchmark that we adopted. The problem for the benchmark solution now is that it's not optimal anymore, because you're not actually simulating the market according to a Gaussian, but you're using a student seed distribution. So this really changed the characteristics of the optimal solution. But still, reinforcement learning is not affected by that, because it's just learning by interaction. So what happened is it can outperform, even though it's less visible the outperformance for the DQN because, as I told you, PPO is known to be a little bit more effective. Where it works in a slightly different setting because it's a policy-based method, but it's definitely more effective than DQN and most of the experiments we tried. But this is just a couple of examples from our paper that gives an idea of what can happen in a simulated setting when you test reinforcement learning over a trading problem. And so the takeaways here are the fact that if you're able to define a benchmark with a known optimal solution, different reinforcement learning algorithm can retrieve that solution in a data-driven manner, and can also outperform that solution when you let vary the original assumption of the environment. But the problem is, what do we do next? So what's going to happen when instead of working in a simulated setting, you work in a real setting? Because whenever you see a lot of reinforcement learning application for trading, most of the time they are based on a specific data set. And you know that in finance, there exists this problem of reproducibility. So it's not always easy to see what's going to happen if now I'm going to change my data set. Is my reinforcement learning agent going to be robust or not? So even though we have seen that algorithms for continuous control like PPO are very performing for this kind of simulated setting, it's definitely interesting in the future to trying to expand this and bring it to the real world, trying to address the challenges, at least for trading. And so it really, this is something that really we need to explore, and we are currently trying to address. So I think my presentation ends here. There is some bibliography. I can share the slides. I think I can open the floor for questions. I went a little bit longer than I expected, but I really wanted to give you as much information as possible.
Thanks, and Alessio. I think it was a very informative question. So, any questions? Okay, you can state your name and ask the question directly. So, Alessio, we have one question here.
Sure.
One question. The application is for derivatives or equities too?
Can you repeat the question? I think I lost you for a second.
Application of the concept is for derivatives only, for even equities to be applied, even in the equities.
Oh, you mean like the asset class where you can apply those kind of techniques?
Exactly.
Yeah.
The asset class I'm talking about.
So yeah, I mean there is no specific asset class. I mean you can. The framework is very general. So in this case, I was simulating returns of equities, assuming that they were equities driven by some mean reverting factor. In practice, being a data-driven approach, you can think about applications where you can also try to use cryptocurrencies or every type of asset. I mean, at the beginning of this presentation, I tried to list a little bit of other application where actually reinforcement learning is used to hedge portfolio of options, or when I've seen applications in the corporate bond market. So there's a lot. There's no restriction in terms of assets, I will say.
So yeah, okay.
Hi, this is Murthy here.
Hi.
See, my question was related to the algorithm. Let's say there are three approaches, right? One is value-based and policy-based and model-based. What exactly you are focusing in the sense, let's say more focused, and what approach is better? Okay, which approach is better if you are trying to follow that? Okay, value-based or a policy-based or a model-based, and why?
Okay, so thank you for the question. So in this talk, I haven't mentioned model-based. So everything that I mentioned is model-free. So model-based is another branch of reinforcement learning where you're actually doing the so-called planning. So it's like a mixture between reinforcement learning and dynamic programming, where you still have a model of the environment and you use that model to interact with your agent. What I talk about is just model free. So in model free, you have two categories: value-based and policy-based. And value-based is when you're just trying to learn a value function to evaluate the behavior of your agent. Policy-based is when instead you're trying to directly parameterize the policy, so the way of behaving of your agent in a direct manner. In order to address the question of what is better, I will say, as pretty much everywhere in machine learning, there is the no free lunch theorem that holds. So you cannot have the guarantee that something is going to work better in any cases. It really depends on the task that you're trying to solve. Then one can say most of the time, policy-based methods, especially within the actor-critic setting, they work better. So what I've seen in my experience so far is that policy-based methods like PPO works better than DQN, but this is not necessarily true in any cases, because what happened after DQN, after that paper of around 2015, is that you have a lot of variance in both directions. So you have a lot of variance of the algorithms in the policy-based category and in the value-based category. So you can really pick among a lot of them, and it can always happen that you test one for your problem, and then a value-based or a policy-based method works better. I will say the difference relies more on not on policy versus value, but on the kind of problems you need to solve. So if the action that your agent needs to take is in a continuous setting or is discrete, because there are certainly some algorithms that can solve just discrete problems. So for instance, DQN can solve only discrete problems where you can take a finite number of actions, because for the way you structured the algorithm, it's a neural network that accepts the state representation as input, and you have as output a limited number of value functions that depends on the action. So the number of action is a finite amount. While instead, for instance, proximal policy optimization, PPO, can solve both problems, can solve both continuous or discrete problems where the action can be defined in different ways. So I will say it's more flexible. It's not just a matter of what is better, but also what is more flexible for your problem. And that's definitely something to consider when you want to pick an algorithm to solve a problem.
Okay. The question continues. Let's say with our motive, okay, whatever your motive, what we are supposed to achieve. So in that perspective, value-based or policy-based you are trying to apply, or both? Okay. Both the policies you are merge and do conglomeration and then get the is it useful for our goal?
Are you assuming that you have a model, you said?
No, I'm not talking about model. You said no need of model, right? You're still sticking on to value-based and policy-based, right?
Yes.
So these two, let's say, okay, can you go back to the previous slide and take away? Yeah, that's no. Go forward. The last slide.
The last slide. Okay.
Yeah.
Okay. So you're talking about this slide. This is actually just related to this application that I show. It's not general. Okay, now I see the misunderstanding. This is when I say that algorithms for continuous control like PPO are more flexible and they work better, it's just related to this problem. Because if you want to solve a trading problem when your action is the actual trading size, which is going to be a continuous value, it's important that you are going to use a reinforcement learning algorithm that can solve a continuous control problem. So the action can be any value any real value in a given environment, in a given interval. While instead, if you use DQN, you are restricted to a discretization of this very same continuous interval, because it cannot solve continuous control problems. So just for this task, I'm sure when I say that PPO works better, but this is not necessarily true if you change your problem. So if you're trying to solve something else, it can be that there is a value-based method that performs better.
Alessio, we have an online question, so maybe I'm
Yep.
asking it directly to you. So the question is, what are the state and action for experiments using DQN?
The very same that I use for PPO. So it's still a very simplified setting where the state is YT, which is the return of the asset that we simulated, and the portfolio coming from the previous time step. So the number of shares that the trader has in the portfolio. So the setting is comparable for all the three algorithms that I show. So DQN, Q-learning, and PPO.
Yeah, hi, Alessio. This is Tejas here. I have a question for you. So,
Yep.
what exactly is the challenges or roadblocks that we are currently facing to actually implement this on real-world data? We now know that it works for simulated data, and we are able to somewhat get the optimal model done. So, what exactly are the roadblocks going forward? Like, what exactly is stopping us from implementing this or modeling the real-world data?
So the challenges are multiple, unfortunately. So the first of all is you don't have necessarily a benchmark anymore. I mean, what you can do is still get like a model that is relatively simple and known as the one we use to simulate the data, and fit that to the real data, so that the solution is not going to be optimal necessarily, but at least you have that benchmark. But it's not necessarily optimal because the data do not necessarily follow this dynamic. So you cannot assume that for real the market dynamic is going to be a sum of mean reverting factors. So this is the first challenge, because you don't have a benchmark and you don't know exactly if you're learning or not. And then it comes into play a lot of different challenges that you may have in finance, like the fact that when I simulate this process, the process is stationary, it does not change its characteristics over time. While instead, if I pick a real financial time series, the characteristics are going to change. So you're going to have non-stationarity problem. You're going to have clustering of volatilities, so regime changes. There's a lot, and there will be much more noise, because real financial data, they exhibit much more noise. So it's definitely harder, and we need to come up with better way to control for this if you want to work in a model-free setting. So if you want to keep the problem as much data-driven as possible. Something that we tried was to leverage on the knowledge of other solutions. Like, for instance, this model here that I'm talking about, this Garliano and Pedersen model, it's based on the fact that if you look at the paper, it trades always less than Markowitz, because Markowitz, it's not a multi-period portfolio optimization, so it's not considering the transaction cost into account. While instead, this model is a multi-period optimization, which considers the impact of transaction costs. So it always trades less than Markowitz. So what you can do is, for instance, computing the Markowitz solution and then using the reinforcement learning to learn the residual of the Markowitz solution. So learning to correct the Markowitz solution in order to trade less and taking into account the nonlinear impact of the transaction costs, which are in equation 15. So this can be some strategies where you blend like known solution in finance with the data-driven techniques, but it's definitely something that one needs to explore more in detail, because whenever you blindly apply reinforcement learning to real data, I will say that it's very hard to get meaningful results unless there is a certain amount of data snooping and you make the data work for you.
Okay, got it. Thank you.
So Alessio,
Welcome.
I have on this regards that what if we apply on the larger time scale, like on the weekly data or the monthly data, then the noise will be definitely less, right? Because that's the actual the moves that we want to capture in the most of the time. So what if we move into the higher time scale? Will that help us? Also, it will reduce the cost, I believe.
Yeah, that's a good question. So yeah, you can certainly use weekly or monthly data. It's not a problem for the setting I described. Actually, I'm simulating data in this example. So you could simulate data and think that they are at a specific frequency. So the frequency is not a problem. As soon as you have equally spaced data over time, that's fine. I guess you're talking about the fact that as soon as you move to higher frequencies, you're going to have less noise. The problem is you're going to also have less data. So for instance, if you start looking at even weekly, and you need to go back to 20 years in order to have enough data points, it's true that you're averaging over weeks, but still you're going to see a lot of regime changes even in weekly data. So there's definitely a trade-off between the frequency of your data and the amount of data that you wanna have. I will say RL it's very important when you're solving high frequency trading problem, because it's really demanding in terms of data. And if you look at the literature that we have seen in the last, I would say 4 to 5 years, there are a lot of high frequency applications of this kind of techniques. So that's where it can really shine.
Got it. I think we have one question from the chat as well. Benjamin.
Well, I just got disconnected and reconnected, so I think I don't have the last question.
Oh,
I didn't see it, maybe.
Yeah, let me see. Okay, it's Matthew's question. So, why didn't you use the Sharpe ratio instead of a risk-adjusted net for PNL as a reward or as a differentiability?
Yeah, that's a good question. Actually, this was a first set of experiments where we decided to use the net PNL. So it's essentially the risk-adjusted PNL without the risky part. So it's just the PNL minus transaction cost. And then for the risk assessment, we were using the Sharpe ratio. Actually, one can have a look at the risk-adjusted PNL per se. They should mirror to the same idea. So in general, when you maximize the risk-adjusted PNL, you also maximize the Sharpe ratio. But it's a good question. There is another paper I'm working on where it's a similar concept, but I started using the risk-adjusted PNL directly. So just the reward function as it is, without bringing into the game another metric. So yeah, that's a good point. It's definitely what needs to be done in this case.
And another question is, there is a follow-up, like in the T student case, do you think the performance metrics should add up?
So when you use a T student in this model, the benchmark is not optimal anymore, because the model holds the optimality of the benchmark model holds when you simulate data as Gaussian. So and this is just one example of a way that you can use to perturb your model. You could do more. Like in the paper, we also tried to actually get rid of the mean reverting factor model and simulate the data as a Gauge process. So you can use a very different process than the one stated by the benchmark models. You can use a garbage process and see if the model can see if the reinforcement learning agent can retrieve the garbage process. So there are multiple possibilities in there. We just tried some, but you can look at the different aspects. So what we are looking here is the data generating process of the data. Then one could modify the objective function, like changing the utility function, make it exponential, for instance, instead of having that quadratic form. You can really do a lot of things, and when you put yourself into this setting where you have a benchmark.
Right. I think we don't have anyone have any question. Okay. So we are good on that. So thanks,
Cool.
Alessio. Thanks for joining us and sharing this session. It was very useful for all of us.
It's a pleasure. It's a pleasure. Thank you for having me.
Thank you. Thank you so much for giving us this lecture for Bangalore team. We are very much excited to looking forward to such more session from you. And we'll also definitely take a look of your paper. Okay, it was a very informative session. Probably I would like to try on my own for my own portfolio optimization, but obviously offline and see that how it is coming. And I have a plan to apply it morely on the higher time scale and see that we can reduce the cost and apply it effectively. Let's see, because 20 years at least we have an index data for that, I believe, not for the short-term stock. So probably in that case, where the stocks are more stabilized, I think we can definitely use this kind of techniques to use for the long term. But when the computer simulation cost is there, definitely is something to consider. But it's really an innovative.
This is something you can do. I mean, you don't feel that you have to stop even if you have a smaller amount of data, because actually I'm trying also to use RL in other contexts other than trading or portfolio optimization. Some more economic context, like how to optimally set the interest rate. And in that case, you have data that are quarterly. So it's a matter of trying, I mean, and see if it works or not, see if it gives insight. So yeah, I'll be open to talk with you even offline about that.
Sure. I'll definitely reach out to you on that.
Great.
We have Guillaume that says great presentation, Alessio. So I think
thank you guys.
Thrilled to have you. Thank you. Yeah, it was really great, and looking forward to seeing you again for the next episode. Alessio, thank you very much for waking up very early.
It's fine. Now I can start my day. It's good.
Yeah.
Great, guys. It was a pleasure. Thank you so much, and have a good rest of your day.
Okay, thank you. Thanks, Alessio.
Thank you.
Have a great day.
Bye-bye.